Okay, let's get started. It's 11:01 Eastern Time AM. Good morning, good afternoon, or good evening, depending on where you are in the part of globe. I really appreciate your support. Hope all of you are doing well. So on behalf of the CAD4Assurance.org organizing committee that includes myself, Professor Gang Ku, Professor Sung Yo, and Professor Jin, I would like to welcome you to the 8th webinar and tool demo for CAD4Assurance.org. I would like to quickly introduce you about this initiative. It will probably take 2 to 3 minutes, and then I'll hand over to Professor Jin to introduce the speakers for today's webinar. This particular effort called CAD4Assurance.org, there is a corresponding website, which I believe many of you have visited. This effort was established in October 2020 during the peak of pandemic to introduce the CAD tools and benchmarks and metrics and publications related to CAD for assurance, which means that the tools which are targeting different assurance issues, particularly hardware security and trust issues in microelectronics. So that was the goal. With that goal, the community came forward and established this effort, and this is truly for the community, by the community effort. And it's basically a web portal for academic dissemination of open source tools, benchmarks, and metrics, as I mentioned. There are right now 55 CAD tools on assurance. Actually, it's probably a little bit more than that at this point. This is a bit dated. Over 1,000 benchmarks. We have 75 contributors, including faculty members, students, and postdocs. And we have more than 7,000 unique visitors, more than 25,000 pages. By any metric, that's definitely very encouraging set of numbers. So it has been a very popular event. We have so far 24 tool demos and webinars encompassing over the 7 events. One course webinar, 3 virtual panels, and all of them have been very, very popular. And we have more than 1,000 registrations, more than 750 attendees. These events are co-sponsored by IEEE CEDA, IEEE Hardware Security Technical Committee, and several companies, including Mercury, HII, and Northrop Grumman. I'm really pleased to have their support and sponsorship for these events, and I'm really grateful to all the organizing committee members, to all the community members who have supported this initiative. So we have good number of events going through for past 1 year, a little bit more than 1 year. I would like to acknowledge the sponsors one more time. I would also like to acknowledge Amanda Osborne and her colleagues in CEDA who are supporting this event technically, and that's great support, and greatly appreciate their help with this. In this year, 2022, we have a bunch of events which are lined up. As you can see, today is the second webinar for this year. The first one already held in February. So Professor Jin would introduce the speakers for today, but I would like to quickly talk about the upcoming panel, that's panel number 4 on securing crypto in the pre and post quantum era, opportunities and challenges. We have 5 really outstanding panelists and an outstanding moderator who are very familiar with this topic. It will be happening on June 10. It's exactly the same time, Friday 11 a.m. to 12:20 p.m. Eastern Standard Time. And I will strongly encourage that all of you attend this exciting panel. As you can see, we are bringing diversity of viewpoints from really different parts of the world. So I'll strongly encourage you to register now. If you are welcome to register today if you are interested, and feel free to circulate among your peers. There is also another panel coming up in the summer, August 12th, in particular, on hardware assurance versus AI, friend or foe. I believe there will be also another exciting panel. We're working on finding the panelists. If you have any recommendations, please let us know. But also for that, I would encourage you to register ahead of time. With that, I will hand over to Professor Jin to introduce the speakers.
Thanks, Sarup. So Just one quick thing I would like to add before I introduce the speakers. So besides this company, we do receive quite a few emails from various companies. They would like to sponsor the events. Since all of us, through me, Gangku, Zhongyu, we are very busy and did not really come up with I would say, a convenient way to accept the sponsors and to promote those companies. So we did not really respond to those requests yet. So we will work with IEEE CEDA and IEEE HSTTC to come up with a better plan. And for those companies who contact us, you will hear back from us very soon. Hopefully very soon. So today we have two great speakers, and their topics are similar. I would say almost the same. I think we did that on purpose. So the first speaker is Lennart Reimann from Aachen University in Germany. And the second speaker is Xiaolong from Kansas State University. So both topics focus on the quantification of information leakage on RTL code. So this is, I would say, this is a very, very interesting topic. And this is one of the few work that really touch the CAD for assurance on RT level regarding the quantitatively measuring the information leakage. People are fascinated on the anything on security metrics, especially if we can quantify how much information has been leaked. So this path will definitely lead us to a very bright future that we can measure the information leakage in the way that like we do inside the channel leakage, but on the RT level code wise. So without any further delay, I would give the podium to Lennart first. And Lennart, can you share your screen and present the tool?
Sure.
Again, just one very quick thing. This demo is tool oriented. So we may not have that many introductory material, but just to show you that how it works. Hey, Lennart.
Perfect. Yeah, thanks for the kind introduction and the invitation for the talk. So I would just go ahead and present my tool. As Jin already mentioned, it's similar to the work from Xiaolong. It was inspired by his work. So I will just skip ahead and present our work that we conducted here at RWTH Aachen University under the supervision of Professor Reimann. So why did we actually conduct this research? The high design complexity and the many parties that are being involved in hardware design might lead to a high amount of design mistakes or malicious modifications, and they lead to vulnerabilities in your hardware design. This means that even secure algorithms can suffer easily from insecure implementations. In our work, as Jin already mentioned, we focused on the RTL design process. So we expect the designer to implement a Trojan, or the actual designer implement a design mistake in the RTL design process, which can then later on be exploited as the end user uses the actual product. In our work, we focus on the confidentiality of sensitive signals, which would, for example, be that we try to quantify how much information from a cryptographic key or user data in trusted hardware components might be leaked to untrusted hardware components, such as shared memories, third peripherals, or third-party IP. And how can we actually assist the designer in securing the design? We could either test the complete chip, but then we would have to rely on the test coverage and would have to be sure that we actually can observe this information leakage. We could work with formal verification, but that is not really suitable for inexperienced user. Or what is coming more and more popular is information flow analysis. So an outlook on my talk, I will give a short background on information flow analysis and quantitative information flow, give then a short insight into my tool, QFlow, show you a little bit about our evaluation for different benchmarks, and then we'll give some more time for the actual live demonstration. It's a live demonstration, so yeah, I hope everything works in the end. And I will then conclude my talk with a single slide. Okay, for the background, what actually is information flow analysis? Information flow analysis or tracking utilizes the non-interference property to make sure that no secret information may flow from trusted or secret signals to untrusted components. So what you normally do is you mark areas in your hardware as highly sensitive and areas in your hardware as lowly sensitive. So highly sensitive signals, for example, could be user data or cryptographic keys. And low signals could just be the clock reset signals or any other inputs which can be observed by an attacker, or later on the output which can be observed in an attacker. The non-interference property would then prove that there is no flow of information from the highly sensitive data to observable output through your digital system. The problem with the non-interference property in my eyes is that it's not really suitable for quite a lot of applications. So for example, if you have an encryption engine as your RTL design, you mark your encryption key as highly sensitive and would then like to use information flow analysis to find out whether information is leaked. The high non-interference property would then disallow you your complete hardware design, because your output here, your ciphertext, which should be observable by an actual attacker as the encryption should be secure. But the non-interference property would disallow it because it still carries information about the encryption key. So what you could do in that case is you try to quantify how much information about the encryption key can actually be found in your ciphertext. More interesting approach would be quantitative information flow. I later on explain a little bit more what it is, but I will not go into much details about the equations. Xiaolong will later on give a little bit more insight into QRI Variable, which we use as an inspiration for our research. It already utilizes quantitative information flow for quantifying the information flow in hardware descriptions. But in our eyes, we found a few vulnerabilities in the implementation. That's why we conducted our own research. The threat model that we are working with is that the attacker knows the complete hardware design. He can observe the outputs of the design and the low inputs, and he may not set any input values himself. So he's actually just observing and trying to look for a leakage of information. Okay, what actually is quantitative information flow? We based our research in that case on the work of Geoffrey Smith. I think I also have a picture of his nice book here. If you are more used to programming and not that much with equations, it's, in my eyes, a little bit hard to read, but it's actually pretty interesting in how you can quantify the flow of information. What you do in that case is you try to compute the leakage. The leakage is the difference between the initial uncertainty and the remaining uncertainty, which in a case would be in how little you know about a secret and how little you know about a secret after you observe the output of your system. So the difference between it and how much information you actually gained would then be the leakage. In our case, we normally call our inputs and output X and Y and work with the following equations. We have the initial uncertainty, which is the maximum of the probability of the inputs. For example, if the inputs is always 1, the actual initial uncertainty or the vulnerability in that case would be 1, because the attacker can immediately guess the signal because he knows the probabilities and would then immediately guess the highest probable signal. And then the probability is simply just 1, which is the highest. The remaining uncertainty tries to compute the uncertainty after the inputs are applied to the channel, so our system. The computational complexity for this problem is actually immense. If you could just compute this joint distribution here, you would just crack every encryption scheme. So we'd have to find approximations to actually compute or quantify the information flow. I will not go into much detail. I would like to more focus on the demo later on. For our tool, QFlow, We have a set of inputs, which is, for example, our RTL code. In that case, we solely work with Verilog code. We would mark our highly sensitive data here, for example, the input inside our code, set input probabilities. So, for example, if different inputs have different probabilities on whether they are 1 or 0, we can set it. And we can mark certain untrusted components in our hardware design. Our tool then passes our Verilog code, computes the dependencies, and merges parts of the different combinational circuits to get more accurate results. We do it on a bit level. We then compute the probabilities of intermediate signals, and later on compute the vulnerabilities with our equations here, and the final leakages, which we compare to thresholds to determine whether then leakages are present or not. In this example here, we, for example, identify a leakage of 0.75, the maximum is 1, of the bit I1 here, and a 0 leakage for the other bit. We additionally can see the complete leakage path, so from what signal to what signal the actual path happens and how the leakage then looks like. Okay, for the evaluation, I will show you some of our results. For the thresholds, we did it similar to Xiaolong Guru. We used a threshold by quantifying the information leakage of 2 rounds of AES, got then 2 thresholds, a warning threshold and a detection threshold, and then later on used them to identify leakages. We used the nice set of benchmarks from TrustHub. If you're also looking for hardware security benchmarks, I can really urge you to have a look at the TrustHub benchmarks. And I can give you here a few examples. For example, the AES T100 benchmarks. We marked the encryption key as highly sensitive, computed then the leakage here. And as you can see, we identified a leakage for the first 8 bits, which was actually a Trojan leaking the first 8 bits in our hardware design, which are over our thresholds. The rest of the encryption key is not leaked at all. For a second benchmark, for example, the RSA T100 benchmark, we marked the exponent at the modulo of the secret key and identified additional leakages for the complete exponent here. The modulo is not leaked at all. We have a few false positives here. I can later on give you a few information about that, but for now, I'll just leave it be. So we identified those leakages as well. Using the leakage path, for example, here, you can then identify the actual source for the leakage by checking out, yeah, it goes from that signal to that signal to that signal to that signal. And either it's then a design mistake by yourself and you might remove it, or it's an actual implemented Trojan. In that case, it's just called Trojan, so you would identify it easily, but an actual attacker wouldn't do it like that. We additionally implemented a few Trojans to compare a little bit better our changes with QRI Variable to then show that certain Trojans are only detected by us and not QRI Variable itself. Additionally, we are able to set the probabilities of input signals, and that's actually pretty useful in my eyes because it helps you identifying actual vulnerabilities even better. In that case, we, for example, have the RSA T300 benchmark, and we have similar results to the T100 benchmarks. We have leakages for the exponent bits. We would then get the leakage path, have a look at the hardware, and then would probably identify a Trojan. In that case, we could elaborate a little bit better on it by checking the Trojan, identifying the trigger condition. And if we identify the trigger condition, we can set the input probabilities of the trigger condition so it actually triggers the Trojan. We did that and then saw that the exponent is leaked completely in that case. So we were sure that we identified the Trojan. In the other case, we tried to remove the Trojan and then elaborate again to see how this leakage then occurs. We still have a few false positives. If you later on want, I can explain you a little bit more on that, how they came up. But for now, we can see that we actually removed that Trojan without losing any functionality later on. Okay, we ran our evaluation on a few more benchmarks from TrustHub to gain more confidence with our design. And as you can see, we actually identified all the different Trojans and vulnerabilities. And as I mentioned before, we have these few false positive warnings for RSA. And as I mentioned before, we implemented a few additional benchmarks to compare with QRI Variable a little bit better, which were not identified in our rebuild of QRI Variable. Okay, I then want to switch to the demonstration. I hope everything works for that. So give me 1 second. I then try to show everything live in here. We implemented a nice GUI for that case to illustrate the usage of our tool and how the actual results then look like. I maybe start with quite smaller example and hope that, yeah, everything works. That's normally not the case if you have to present in front of a few people. So yeah, I start with a small full adder. And as we can see, we are working here with a schematic. If people of you already familiar with, for example, using Xilinx tools or Vivado, then from Xilinx, you normally have then graphical user interface to have a look at your RTL code of your hardware design, for example. We can also here then show us our Verilog code. As you can see, it's a pretty fairly simple full adder. So you get a sum output and the carry output for your case. On the left side here, you can set the different parameters for our tool flow. You can also just call our tool from a terminal, of course, but for this case, we try to work with the GUI to actually understand or illustrate the usage. What we would do then is we compute the leakage from a signal that we mark to all outputs of the top module, because we don't want to leak any information that is secret in here to the output ports. So how that would look like is we just take, for example, one of the, maybe just let me make it a little bit bigger. We mark one of our here input signals, full adder A. It's one of the operands in that case. We mark it as taint. We can see it in here. So that's our currently highly sensitive data, which we then want to run QFlow on to compute how much information from that signal is actually leaked to the two output ports which are available. Of course, it's just a full adder, so you can expect a high leakage of information. So we would just run QFlow in that case. We can have a look at our results, which are, for example, then just a simple report. We have detections of one leakage path. Mark none of them as secure or none of them as warnings. And as you can see, we also have a quantification in here. For example, for the carry output bit, we have a leakage of 0.75 of the actual input that we marked. And for the sum, we have a leakage of the complete bit. I will show you now how that actually looks like in the design. We can mark here our full adder bit. Give me a second. I just have to maximize it again. Our leakage path, we can see here directly in our design. So you would be able to understand it. Additionally, you can see it in text format here at the bottom. So you can then have a look at it at your Verilog code again, and then understand how it actually happens. Why do you have a leakage of 1 bit for the sum and only of 0.75 for the bottom? As I mentioned before, you have some signals which are marked as low and some as high. So we have this A signal which is marked as high, and the remaining inputs here and the outputs marked as low. So we know what those values are for that cases, and the values are for the observable outputs, but we don't know what the secret is. But if we know B and the carry in bit and the sum output, we immediately also know what A is. That's always the case. It doesn't matter what B, C in, or sum is. If we know them, we also know A. But the case for C out is, yeah, it's not the same case. For example, if we have a C out of 1, a C in of 1, and a B of 1, it doesn't matter what A is. It's still C out of 1. So we have to guess in the end if it's 0 or 1. So we lose information from A to the C out in that case. If we ever want to have a closer look at the leakage path from A to C out, we can, for example, just reset our parameters again, set our taint source again, and then mark, for example, this output here as a trusted target. So we trust some now. For example, a component is connected to it that we just trust. It's our component, we implemented it, and it's safe. So we would run QFlow again and would then see that our new leakage path that we found goes actually to the carry out bit. That's a new, most significant leakage path. What we could do now additionally, if you would just let me, give me a second, we could mark the same signal again as sensitive, mark the same output again as trusted, and then could add, for example, probabilities for the input. In that case, it would, for example, be full adder dot B, and I have a look at the 0 bits and then want to give it a probability of 0. Additionally, we can do it the same for C in, and then would run QFlow again. Suddenly we have a leakage of 0 bit to C out. That's also logical. For example, a probability of C in of 0 and a probability of B of 0 means that they are always 0. B and C in are always 0. And then again, it doesn't matter what A is. The carry output bit will always be 0 as well, because you need at least 2 ones to have a carry bit that's 1. So you can play around with the probabilities, which is pretty useful, for example, for setting trigger conditions or for setting reset signals, which are far more likely to be 0 than 1. So you get more realistic computations for your actual implementation. Okay. As I mentioned before, maybe I have a last example here for this benchmark. We mark the input again. And as I said before, we merge our computations. So we merge how many combinational parts here are computed together. So how many of them form a single lookup table, a single channel, to compute the most accurate results. We can't have a too big lookup table because then the computational complexity would be too high. So we have to limit how many of them are computed together. The rest needs to be a little bit approximated. If we reduce that value, we get less accurate results, but at faster runtime. So if we compute it again, suddenly our leakage for the C out is not 0.75 anymore, but 8.9. That's because we have to approximate a little bit. And every leakage after every gate is computed anew, and then they have to be combined. But we try to form our approximations so that we try to overestimate the leakage, so that we introduce false positives, but not false negatives. We could then have a look at the leakage path again, but yeah, I already showed you that. I want to show you now a more complex benchmark. So I just opened the GUI up again. And as we use Python script, most of the parts are not that fast. It's mostly for academic research. So you have to have a little bit patience here. So we open it now. Seems like it's working. So we have our AES Trojan-free design. As you can see, it's much bigger than the other one. We have the different expand key, the different rounds, which you would expect in your round 1, round 2, round 3, in your hardware design. And what we could do then again is we mark our key, set it as, I have to shortly move the zoom feature at the top, otherwise I can't see it. So I mark the source, all bits again, and then start QFlow. The problem is now, if you have a look at my paper, the runtime is not 10 seconds as it is for the small benchmark. It's a little bit longer. So that's why I already prepared the results for that. Give me 1 second. I have to move it into the screen here. So I already ran the computations here. And as you can see, there are no leakages detected. That's because the key runs through all the different rounds. And if there actually would be a high leakage, the complete AES implementation wouldn't be secure. In that case, we find out it's secure. So if we have maybe a look at the results here, we can see that the leakage for the different key bits, we do it bit by bit here, bit 0 to 127. So it's AES 128. We can see that the leakage is actually fairly low. It's still overestimated probably to the actual leakage if you would use the complete quantitative information flow computations, but you would also calculate probably for several years. So we over approximate a little bit, and as you can see, the leakages are fairly low compared to the threshold. They are then lower. That's why we don't identify any leakages. For a different benchmark, we could have a look at. I have to open it shortly again. It's the AES T100 benchmark. So it's the same AES design, but for the benchmark, we actually TrustHub actually. They implemented a Trojan additionally in the design, so you can test your tools whether they are able to identify leakages. So we have the AES design I showed you before. Maybe I can open it. Our placement and routing is done in time, so it sometimes takes a bit. As you can see, the design kind of looks the same, but we have this additional module. Give me a second, I have to find it again. Yeah, the additional module here, Trojan. And what we would then do again is we mark our key here, set the tane source, so the highly sensitive data again. We could again play around with the probabilities for the reset signal or for the state or for the clock. We could mark certain outputs as trusted or mark additional signals in our hardware design. So normally all our outputs of the top module are marked as untrusted, but if we don't trust certain signals in our hardware design itself, we can also mark them as untrusted and then run it again. So we would run QFlow again, as I mentioned before. It takes quite some time for the computations. So I switched to some window I opened before already again. We have, okay, I opened on the wrong. So yeah, so I ran QFlow already. What we could do then again is mark a leakage path. As you can see, I can mark it for, we identified 8 leakages. I already showed you on the slide that we have 8 leakages for the AES T100 benchmark. We could then just start clicking around and mark the different leakage path. As you can see, currently you don't really see a difference when I'm clicking for the different leakage paths. That's because they all go through the same signal. But if you actually open up the Trojan, which hopefully works perfectly, you can see that the leakage paths go through different XOR gates and then are combined again in a register. So if I start marking different bits again, you can see that you actually mark more and more of the actual leakage path. You can identify them. You actually have it in text format here again, and then open your Verilog source files. For example, it starts at top key. You can open your top file here, see, oh, it's key. It goes into the top Trojan. So you can see it, oh, it goes in here. Open the actual Trojan. That should be this module. And continue your path through your actual hardware design to identify the leakage and then understand how it comes to that problem. Is it a malicious modification or an actual design mistake? As a side note, if I then would mark the additional output here, capacitance of the Trojan of the hardware design as trusted again, it would then, for the computation again, would be the same as having the AES Trojan-free benchmark. Okay, I would be done with the demonstration, so I have a last slide. Give me a second. I don't know the number, so I can't skip immediately to it. So yeah, for the conclusion and the future work, I just presented you our tool QFlow and the GUI that we are using it for it. QFlow conducts our static quantitative analysis using approximations of quantitative information flow to analyze hardware description and determine information leakages in our hardware description. So it would be useful for cryptographic accelerators, hardware storing user data, and similar hardware architectures. As I hopefully illustrated with the GUI, QFlow can easily be integrated in existing EDA tools, for example, Vivado, or additional tools that already have a graphical user interface for hardware descriptions. We do our quantification in a bitwise fashion. That's mostly because in our eyes, it resulted in a more accurate implementation. And we thought that the results, for example, 0.5 and 0.7 are easy to understand and actually a nice metric to understand the information leakage. And as I showed with the benchmarks for Trust Hub that were available for our attack scenario, that we had no leakages that were overlooked. And for future work, as I mentioned before, we have a few false positives for the RSA benchmarks, for example, and we are currently working on removing them. We already have an implementation where we actually remove them, but it's not public yet. So yeah, I hope that we continue our research in that field. It's actually pretty interesting, but I think that there's still a lot of work to be done so that we have suitable metrics for quantification. And we would also like to broaden the attack scenario. As I mentioned before, we say that the attacker cannot set any input values and that he can only observe. It would maybe be a little bit more interesting if you can actually, for example, set the trigger, and then it would change your quantification because then the vulnerability would be much higher. Last thing I want to mention is I want to give a special thanks to some of my students, Luca Hanel, Zab Erdenes, Anshul Prashar, and Evgeny Rezunov for all the help in my research. Okay, that would be everything for me. I hope that, yeah, everything was audible, and yeah, thank you for listening.
Thanks, Lennart. So I forgot to mention at the beginning, if you have any questions, please use the Q&A button to type in your questions. So far, we do have 2 questions. One is in the Q&A bar, one is in the chat window. Kevin, could you please retype your question to the Q&A bar? You can click that button at the bottom of the Zoom. So we still have time for a few questions. So Lennart, can you quickly read the question and from the Q&A window?
Yeah, sure. So the first one would be from Jason Oberg. Yes. How do you calculate the probability computations per gate? Each gate would have a different probability for passing information from a particular input to particular output. Yeah, that's actually fairly simple. The most stupid approach, or the fairly simple approach, would be to have a lookup table. And for every gate, you would just know if what bits would result in what outputs. And then if you have the input probability, you could then compute the actual output probability. We try to merge many gates together to form bigger channels. So we have then, of course, bigger lookup tables, but it also results in more accurate results, because if you have inter-signal dependencies, the probabilities depend on each other. So you get more accurate results if you form big clusters. But if you form big clusters, the problem is also that you have more computational complexity. The next question that I saw is, does QFlow handle feedback in RTL? The demonstration all seemed to be feed forward. Feedback in RTL, do you mean loops in your hardware description? Currently, we handle it as we only work with data flow graphs. So loops would be a little bit problematic in the case that they might be ignored. We also have these RSA benchmarks, for example. That's where the false positives come from. For example, the RTL RSA implementations keep on using the same intermediate signal over and over again. And only after 12 rounds or something, they write out the signal. But what QFlow only sees is that you go in and the intermediate signal is connected to the output. That's why we have those false positives. So we currently don't fully handle feedbacks or loops in our hardware, but we are working on it, like implementing QFlow a little bit more timing sensitive, so that we actually unroll those loops and have more accurate computation than remove those false positives. Okay, how does this work related to taint analysis? It works sequential circuit with feedback. Okay, I hope I answered the second question already with the feedback. Currently, we don't handle a sequential behavior that perfectly. It has false positive caused by a sequential behavior, but in future work that we are currently submitting at conferences, we are already trying to deal with that issue. Of course, the computational complexity increases because we have to unroll data flow graphs and have to do recomputations. But yeah, we are trying to work with it, but currently it doesn't handle it. Yeah. How this work relates to taint analysis? I'm not familiar with that term. It depends a little bit on what you mean with it. If you just mean general information flow analysis where you don't quantify, it has similarities that you forward your taint or your information flow tracking, that you forward the taint symbol through your circuit, but you actually don't quantify in it then. I'm not sure about taint analysis. How do you come up with a threshold? Yeah, we actually got inspired from Xiaolong Gu's work when they cited the book about AES, that 2 rounds of AES should be sufficient to obfuscate a signal. So we implemented a circuit with 2 rounds of AES, ran QFlow over it, and the final values that we got we used as a threshold. Depending on how you're working with later on, you can set your own thresholds. In the GUI, I didn't really go into detail with that, but you also have on the left the possibility to set your own threshold, but the default would be 2 rounds of AES. Okay, that would be it in the, does it differentiate?
There's one more question.
Oh, yeah.
Differentiate the explicit.
Does it differentiate between explicit and implicit flows? Yes and no, that depends a little bit. For example, timing channels would be a little bit more implicit flows and not explicit flows. Currently, the tool doesn't, for example, support timing channels, but the general influence of your secret signal into the selection bit, for example, of a multiplexer is used, but we actually don't really fully differentiate between it now, currently. We are having research being done on having also static analysis of timing channels and identifying them, but that's also not public yet. Okay, I hope I answered the questions. It's sometimes a little bit hard to understand them from just a few words, but yeah. If it didn't answer all the questions, I think you might find my paper and then also my email address, so feel free to contact me. Okay,
yes,
that would be it from me.
So do you plan to release the tool, this open source the tool?
Currently, it's still quite buggy at some points, and we are fixing it. So currently, there's not the plan. We are still discussing it internally, but I'm not sure what the future brings. The research and the equations are all online, so you would have to re-implement it yourself. That's what we try to do with QIF Variable. But currently we are not planning to upload it.
Okay, good. So there are still some questions, but my suggestion would be you type the answer.
Okay, I will do it in the background.
Yeah, thanks.
Perfect.
So many thanks to Lennart. Now it's the turn for Xiaolong Guo. I think Lennart already introduced Xiaolong for me. So Xiaolong came up with this idea that leverage the information theory to quantify the information leakage on RTL code. And as I mentioned, this opens the door of a new research direction. And now I would leave the podium to Xiaolong to introduce his original idea and what he has developed so far.
Okay, thanks. Okay, let me share my screen. Thanks for Lennart's work. I also have some ideas. Maybe we can discuss offline. For my presentation, today my student Zhao Liu and I will introduce a QIF Variable and the if tracker. You can treat it as a new feature of the QIF Variable. It's our latest work, and this work is collaborated by the Orlando Iris and Dr. Jin from University of Florida. And first of all, thanks again, Lennart. So basically, both of our work exactly share the same attack model and the background. So I will skip that part or go through it very quickly. In the background, I will introduce some different like data flow graph. And then I will give a very top level description about the tools, QIF Variable and the if tracker. After that, we will mainly introduce the demos for the QIF Variable and the if tracker. So let's start. First of all, for the attack model, we share the same attack model with the QFlow. So let's skip that part. Basically, we assume that the bugs could be introduced by the developers or the attackers in the RT level hardware design. And our QIF Variable, it's used to detect the vulnerability that can lead to the sensitive information leakage, while the if tracker can cover more attacks than the information leakage. We'll show it later. And first of all, let's take a look at the data flow graph. I will not introduce the information flow since it has already been introduced in the QFlow. So in the data flow graph, all the nodes, in fact, all our QIF Variable are based on track the information in some data. This data is the data flow graph. And all the nodes and also the tint analysis is a common used data flow analysis techniques for realizing this kind of the information flow tracking policies. And all the nodes in the data flow graph are untinted initially. Then we define the tinter source. which is some nodes as the source of the propagation. Any nodes which is derived from a tinted source can be considered as tinted, while others are still untinted. We call this procedure as the tinted propagation. And the tinted targets is another group of nodes, which are the destination of the propagation. The tint policy provides the rules of the tint propagation, such as when the propagation will be terminated. Once the tint propagation arrives at the tint target, or all the propagations are terminated without arriving at the target, we can treat it as we get some conclusions from this analysis. Using our tool, the data flow graph is generated from the abstract syntax tree. In short, we call it the AST. And the AST is parsed from the Verilog design. Yeah, we are also working on the parser to try to cover the system Verilog to our framework. And since the AST keeps all the information of the Verilog program, it provides more space for us to analyze the more complex behaviors of the hardware. That's why most of our work rely on the AST. So back to the QIF. Yeah, as introduced in the QFlow, QIF means quantitative information flow, so it can quantify the leakage information through calculating the entropy. In the QIF Verilog, a matrix called remaining uncertainty is designed to terminate the propagation. In each step of the propagation, we apply the remaining uncertainty and accumulate it. A larger remaining uncertainty value means a more secure propagation path, so that the propagation will be terminated once it is larger than a threshold. Further, a major portion of the propagation we find is in fact in the information flow tracking is under some preconditions. It's like the implicit information flow. So only under that condition, then the propagation can be happened. So we investigate these preconditions and summarize it and then analyze it. So and also we develop this functionality as the if tracker. So let's go ahead to take a look at the QIF Verilog first. So in this tool, the front end of the QIF Verilog is part of the that the user can access and type in their codes. So in the back end, the real data processing is happening there. And the QIF Verilog is designed by extending one new tab from the standard Verilog, and we denote this new tab as tint. In practice, the designer without any security background can only need to figure out where is the secret and then label this tint type. And in fact, the denoted new tab tint is just to tell the backend that which signals should be protected. In other words, where are the tint sources? So in our demo, we will not show this front end. We just denote the tint in our backend and run our software. So in the backend, the information flow tracking is performed and the remaining uncertainties is utilized to detect the information leakage. And here is the structure of the QIF Verilog. At first, QIF Verilog parses the HDL to the AST to the abstract syntax tree. Then it traverses the abstract syntax tree and generates a data flow graph subset for each signal. We use the pVerilog for all above procedures. After that, our tools reconstruct the whole data flow graph by connecting all the data subsets together and then build a directed graph. This directed graph contains all the relations among signals. And in this step, the user can denote the tint source. Of course, the tint targets are the output port for RT level hardware design. Then we start the information flow tracking along with calculating the remaining uncertainty. We'll show the details in the demo. We add the feature vulnerability locator to locate bugs in the Verilog code. Since all the line numbers is recorded in the AST, so we can track those line numbers along with the information flow tracking and then record it when detecting the bugs. The next, we add another new feature to extract the conditions of the propagations. In most of the time, the conditions are associated with the if statement or branches in the AST. So we call this tool as the if tracker. As shown in the figure, a successful propagation from a source to a target must satisfy several preconditions. Through track backward, we can infer the input that can lead to a specific propagation. By now, our current progress is we can associate the input instructions with the specific signals in a CPU design. And compare with the existing information flow tracking approaches, the if tracker can increase the efficiency and reduce the false positive significantly. Because in fact, some of the propagations, even if there are propagation paths there, but it will never happen because there are some conflicts among its propagation conditions. So we have compared the if tracker with the commercial tools like the Jasper Gold and the VC Static for detecting the malicious insertions in the SOC platform. And as a result, our tool has a better performance in disclosing the Trojan triggered by the sequential logic. For more details, please refer to our data paper this year. And again, PyVerilog helps to generate data flow subgraphs in the structure of the if tracker. And the directed data flow graph reconstruction is as the same as the QIF-Verilog. Based on the directed graph, the if tracker extracts the tinted propagation paths along with the propagation dependencies or propagation conditions. In the end, the if tracker checks the propagation conditions to delete the repeated or unreached paths and then verify the potential violation of the information flow policy. The same as the QIF-Verilog, we also provide the bug locator for the if tracker. And the next, let's show the demos for both the Verilog and the if tracker. So let me let my student Xiaolong to do the demo.
Hi everyone. So I will show the demonstration of the QIF and if tracker. So since the if tracker is the follow-up work of QIF, so we add some new feature to if tracker. So I decided to present both separately. So let's start with the QIF. Yes. So here is the QIF help menu. So like I mark here, so for user, we should use the desktop level to declare the top module of the design and along with the input file. And since we utilize the information flow tracking technique, so we need to specify the 10 source and 10 target, which is the propagation starting point and ending point. And we can also use the dump path to dump the detail of the 10 propagation path and render the graph to see the entire data flow graph. And we can also use the option called use arbitrary signal, this option, to check all possible paths from input to the output. And we will summarize the result using the dash summary option. Yes, so here is the overview of the QF tool. So I will run the QF on two test cases. The first one is the DES Trojan free, and another one is DES Trojan in. So the main differences is just let me show you the difference of two. Yeah, so the main difference is the DES Trojan in file has two actual modules. One is the Trojan trigger, and another one is the AM transmission. So which means that the sensitive data, after the Trojan being activated, the sensitive data will be leaked through the AM transmission payload. And we are trying to detect this anomaly by using our tool. I have already prepared two shell script to running this test, and let me show one of them. So like I mentioned, so we first declare the top module, and this time we use arbitrary signals, this option, which means that we didn't know. So suppose we didn't know where the leakage will be happen, so we will track all possible paths from the input to the output, and we will dump the data flow graph and dump the path, and also dump the line number, which we can, based on the line number, we can refer back to the source code to see where the maybe the most vulnerable part in our code. And here for this script, we run the DS without children one. And for the another script called the demo QIF vulnerability, we run the DS within the children. So since both script will run maybe more than 5 minutes, so I have already recorded the result. So that I can have time to demo the second part. So let me directly show the result now. So we have the output directory called the DS _0. That is the output directory of one experiment. So as you can see, we have several files, the graph file, which we use in the dash random graph to generate, and we have the path file. We have several path files. Each path file shows the detail from some specific source to specific destination. And we also have a summary file. That is the most important file I will introduce. And we also, the pre-processed file, that is the pre-processed result of the design. Okay, so let's take a look at the one of the path file. So the name shows that we will track the signal from the key to the DS out. So like after the encryption. Okay. So here is the path file. So we can see that we showed, so the 10 will be being propagated from the key to the dash out. And also we also generate some temporary node, which it has been involved in the 10 propagation. And we will record the weight, that is the QF metric, the Reimann uncertainty metric. And we also calculate the accumulated weight and the line number. We also record the line number. So like for example, here is the in code line 206. So for the path file, we will record the weight, the accumulated weight, and the line number. That is one of the example. I know that it's not so, it's a little bit hard to understand this path file, because actually we use this path file just to refer back to the code, and we mainly use the summary file to find if there is some vulnerability exists. Okay, so let's take a look at summary file. Yeah, so the summary files, so there are 4 entries in the summary file. Each entry represents one possible path from a specific source to the target. Like for the first entry I marked here, we found a 10 propagation path from the DS input to the DS output. And we also calculate the minimum RU and the threshold. So based on the minimum RU and the threshold, we can give an evaluation to conclude how the safety level of the path. So for this summary file, we found four possible paths from different source to the target. So I think I need to open to another summary file. So with the DES with the chosen inserted one. So like let me show you the differences. So that is another output directory which is generated based on the chosen inserted design. So we have we still open the summary file. So we can compare, we can see both summary file in the window. So like take the second one, for example, for the entry I select here, we find that the source is DS in and the target is DS out, and we calculate the minimum RU is 34 and compare with the threshold, which is 160. So we think because the minimum RU is lower than the threshold, so we consider it as a vulnerable path. And we can see so obviously we can see that. So for this entry that I select here, the program have already helped us to select the most vulnerable path, because the key, the source target is the key input, and the target is the antenna, and we only have the minimum RU is 2.5, but the threshold is 150, which means that the minimum RU is much lower than the threshold, and we also consider that is the most weakest path. So based on the summary file, we can easily identify the vulnerable path, and we can refer back to the path file to find where the vulnerable code. So that is the path file and the summary file. And I also prepared the data flow graph. So for each data flow graph represent the entire data flow graph, but we will mark the propagation path. Let me switch to another window. So here is the entire data flow graph of the DES module, but since because it has a lot of S box, so we cannot show them in one screen. So I can only show part of it. Like for example, here the entire data flow graph, we pick a 10 propagation from the run select, and we propagate the 10 through the right arrow, and we just go through just to the destination, like the DS out. So, and we will calculate the weight through each step. I also prepare another one, so because that is a large design, so it's not hard to it's hard to see. So so for this one, it's a test. It's a very simple module. So our expected data flow graph, it just tells you how signal being propagated from the source to the target. And we also calculate the weight accumulatively. So that is the data flow graph we generate. So that is the first part. So about the demonstration of the QIF, and I will continue my demonstration with if tracker. Just give me a second. As I mentioned before, so if tracker is share the same front end with QIF, so we still have some same argument we use to operate with the tool. Like for example, we still use the dash top level, the dash 10 source, 10 target, and the random graph dump line number. So I won't introduce this detail in the demo of the QIF tracker. So I will mainly introduce another argument called the dump constraint. So that is that is how. So we will utilize this argument to extract the propagation constraint. Sometimes we refer it to the maybe explicit data flow or implicit data flow. And we still prepare another test case to show how we utilize this option. So let me switch to another window to show you guys the experiment setup. Yes. So we use a small SOC as our test case, and here is the overview. We have a processor which can write and read to the shell crypto core and RAM separately, which means that neither RAM nor shell crypto core are allowed to read data once the CPU is writing to one. So we not allow both slave IP to read data from the bus simultaneously, because that is a shared bus-based interconnection. And traditionally, we add an extra logic in the RAM so that RAM can steal the data from the bus, which means that once the CPU is trying to write data to the shell to write some sensitive data to the shell core, and the RAM can steal data, can eavesdrop the data. So that is how we design the experiment, and we will try to use data flow analyze to find this vulnerability. So basically we will run two tests. two paths, like the to 10 propagation. One is from CPU to the Xiao crypto core, and another one is from CPU to the RAM. So that is basically our experiment setup, and I will run two separate.
Yeah. So sorry to interrupt. So for this example, basically, is a typical example we designed for validate our tools, because this example includes also conditions to let the propagation to go through. And the key point is that there, in general, when a bus is when SOT is running, two information flow cannot be existed at the same time, and our tools will validate this anomaly by analyzing the conditions to let both information flow tracking propagation exist in the same benchmark. So that's a key point. Yeah, Zhang, please go ahead.
Oh, yeah. So yes. So as the Professor Guo said, we think the data flow graph is a little bit limit to analyze this situation. Yes. So we have shared the terminal now. Yes. So I still prepare two scripts, and I will explain one of them, and we will run the tests simultaneously. Yes. So here is how we set up our test. Like we still declare the top module, and this time we will declare the 10 source and 10 target, because we only we only care about this 10 propagation, and but we still don't know where the children inserted, and then we will use dump constraint to find the propagation constraint or the conditions, and that is here is another one we for this one we still run the same, but this time we will one is run shell one we declare the 10 target is the RAM, and another one we declare the 10 target is the register located in the shell crypto core, and we will run both. Yeah, so it won't take too much time because they don't involve so many. We won't reuse so many modules like the crypto cores. And the idea is, I think the Professor Guo has mentioned, we parse the source code into the data flow graph and doing the further analysis. Yes. Okay, so maybe my first look at the, so we have two separate. Yeah. Top one is top. Yeah. So we will mainly compare the constraint we extracted. So for example, we just see the yes, I will switch the slides. So like I have already reorganized these things, and but I will firstly to explain maybe a little bit. So here we have a 4 entry, which means that we find 4 paths from the source to the target, and and you can see the 4 entry are identical. So I will mainly elaborate one of them. So take the first entry, for example, there are set of conditions that we extract from the 10 propagation. Like, so for first one, which we need the signal called the current SAXI W ready, write ready, should do an operation with write valid, and the result should be true. So that is so the propagation, if we want the propagation succeed, we need to satisfy this condition, and we need to satisfy all of them to make the propagation successful. And the same here, we still need still require both those conditions to be successful. And I will switch to because we don't pre-process this result, so I will switch to the slides to make things. Yeah. So here is our analyze based on the output result. So figure 1 is the time propagation from the CPU to the shell crypto core. The second one is the propagation from CPU to RAM. And we also select the part of the result, the constraint, because most of them are identical. And because why they are identical? Because they are following the same AXI protocol. So here for the second one, you can find a very interesting thing. That is where we insert the malicious logic. So condition 2 shows that we require the slave register write enable signal need to do all operation with the constant value 1, and the result should always be equal to true. And that is always equal to true because any value do all with 1 is always equal to true, which means that we get rid of the signal write enable. So that is where the malicious behavior is happen. Like because for RAM don't need to depend on the signal read write enable, so he can constantly steal the data from the bus. So we can resolve this condition we can solve the conditions to get to find this vulnerability, and we can further go back to the code and to find. Actually, that is the control flow things. Yes. So that is the whole demonstration of the if tracker. Yeah.
Yeah.
So,
For the final step, all the conditions now we are working on it to try to automate the analysis for those conditions using the SMT solver. This is our future work. And another point is, so since all the instructions for CPU, they place like the OP code or program, they place most of them are in fact in the implicit flow. Therefore, the if tracker plays a very important role in analyzing the CPU-based the CPU benchmarks. And also for a question to the QFlow, I think it's also for question for us is the temporal logic. For temporal logic, now in fact we have already added the timing stamp to our tool, which means that when we track the information flow, we can have the clock cycle after each propagation. But we do not prepare the demo for it. So hope you can you can pay attention to our future work. Thanks.